Hello physics students, this is just a quick video to explain the shortcut that I took in some of my working. Basically, what I'm looking at is in a previous problem, which is this problem here, I said u is equal to 0. I won't go into the details. Of this problem was a mass of 90 kilos has a net force of 450 newtons applied to it over a time of 4 seconds. What is the final what is the change in displacement, the change in velocity? Now what's really key here is, now I simplified it by saying u equals 0. That's actually not correct, because we don't know what the initial velocity is, and maybe I shouldn't have taken this shortcut. It's just kind of a habit. I know already that a change in velocity is equal to at, and a change in displacement is equal to half at squared, but I want to go through and prove that so that you can see that as well. So what that looks like is, and I'm doing this in more of an algebraic fashion, so if I've got a change in speed, the way our equations of motion behave when we are doing a change in speed or a change in accelerate, so we're accelerating and we want to know the change in speed and the change in displacement. What this looks like. So u naught is our initial velocity. Initial velocity is always when we define time equals 0. So we've got a problem and we're saying we're accelerating by 4 seconds. Well, time equals 0 is the point where we start accelerating for 4 seconds. So I didn't have my pointer on the previous page, apologies for that, but here I am. So this is what the world looks like at time equals 0. At time equals 0, our initial velocity, I'm just going to say u naught, our initial speed v naught. So what is our initial speed at the very beginning when time equals 0? Well, it's going to be equals u naught plus a times t naught. We don't know, well, in this case we can work out a in the previous problem, but let's say we don't know a. Well, our initial velocity v naught is equal to u naught plus a. At the very beginning, we've defined time equals 0 at the problem at the beginning of this event, the situation. So because time is 0, that acceleration is going to disappear. Same with our initial displacement. Initial displacement is u naught, like our initial velocity, times our initial time, plus half a initial time squared. But our initial time is 0, so that all works out to be 0. At the end of 4 seconds, or the end of a period of time, our new velocity, v1, is equal to our initial velocity. The initial velocity doesn't change. It's always the velocity when we started to accelerate. That's really important to understand. I've heard discussions previously where there's a misconception there. So it's going to be our initial velocity plus our acceleration times how long we accelerated for, time. Our displacement is going to be our initial velocity times our new time plus half at squared. Yes, I just had to think about that for a second. So that is time equals 0, and this is time is at t1. And in this algebraic version of it, the more abstract version, I haven't gone through and defined exactly what these times are, because what I wanted to demonstrate was the following. The change in velocity is our final velocity minus our initial velocity, which is our final velocity is initial velocity plus acceleration times time minus our initial velocity plus, well, I've said over here it cancels to 0. In other words, the initial velocities cancel, and our change in velocity is our acceleration times time. And that's really important. Our change in velocity is acceleration times time. Our final velocity is whatever our starting velocity was plus the change. That's what this expression says here. What is our initial velocity plus the change in velocity? Finally, and I actually now want to go and have a look at the formula sheet, but I'll come back. I'll check that in a second. So our change in displacement is our final displacement minus the initial displacement. Go through the same working. Well, the initial displacement completely cancels out because our initial displacement was defined when time equals 0. So therefore, our displacement at that point was 0. And so it's our initial velocity times time plus half at squared. Now, you can't see this, but I'm just going to bring up the QCAA physics formula sheet. And actually no, I can't share this on my computer at the moment, but if I'm looking at the QCA physics formula sheet and I go to the equations of motion, linear motion and force, all the equations are in terms of absolute. So it's final velocity equals initial velocity. Pause the video, bring up the sheet, and then come back to me if you want to, and come back to the video and I'll explain what I'm looking at. So under the section linear motion and force on page 2, we have v equals u plus at. That is final velocity is equal to our initial velocity plus at. At is the change in velocity. Displacement is equal to our initial velocity times time plus half at squared. That hasn't really changed. Technically speaking, we should be saying S is equal to S naught plus ut plus half at squared. In other words, the ut plus half at squared is actually our change in displacement, not our absolute displacement. So it's interesting that they do it that way. And then there's some additional formula. So I probably like to think it more in terms of what is my change in velocity, what is my change in displacement, so that we don't get confused with initial conditions. But that's how they have done it. So that is pretty much it. So that's all I wanted to go through. I don't actually check the comment feed on these videos, but if you have any questions, you feel free to ask. Otherwise, all the best with your studies.